Yeah, where are those signs? Overpressure, viscosity. This one, the viscosity corrections, KV, and so on and so forth. So in this case, yeah, there is no viscosity correction, and then there's also discharge coefficients, the CV of the thingy. This CV, if we go to the gas, so this CO is then the CV. Back pressure coefficient is 1, differential coefficient is 1, so it's all by default. And then I select the orifice of T, so this T is then the size of the one that we size in the other page, yeah, and this safety analysis page. So we know what the size is, and then we just put it here, and then this orifice will then be calculated accordingly, or found according to this type of this orifice. So we can have it here, and then there is also one thing. In this case, I set the pressure to 4.4. So yeah, like imagine that we have a design pressure of the vessel to be like maybe 4.5 or 0.6 something. Yeah. So we let the set pressure means I looked through the Aspen HYSYS help. So the set pressure is what we understand. Where the pressure, if the pressure reach 4.461, and then this valve will open. But then it will not open fully, yeah, instantaneously. It will open fully if the pressure in this vessel goes to 4.5. I just put 4.5. You can put any number. Yeah, and then this is then the CPCV, the pressure flow model that we typically do, and then rigorous. What else? Yeah, it's a quick opening. Because I don't want to have the valve to be in linear or equal percentage. It has to be very quickly open. And then that's it basically. Yeah. So because we have the design, we have the size, and then we have the set pressure, and then the full open pressure. We could also put the same number here and there. Yeah, it's in symmetry. I don't remember if we have this. Yeah, it's a much more straightforward in symmetry compared to the HYSYS somehow. And that's it. So what I did, so let's just run this. Yeah. Is that factor 60? Okay, let's just run this, and then and then we'll see the pressure. So this pressure, because the set point is 3.5. Okay, so 3.5. So it's now ramping up to 3.5. So we just have to be patient a little bit. So while waiting, I did run this model. Put it here. So in case you would want to go through this relief sizing, and then I already have the slides. So these are the things that I've mentioned to you. Right. So the sizing, and then the set pressure, and I did run this. You can see this. So we have the PC PIC control. Yeah. The blue one is then the operating pressure. The blue one is then the operating pressure. And then the I'm confused. Oh, sorry. PV is then the process variable. Yeah. So the green one is then the pressure that we have in the vessel, and then the blue one, I don't remember. Maybe we can do the simulation again. 1 minute. Yeah. Set point is the red, so set point is 3.5. Yeah. And then process variable, the green one. Yeah, the green one is then the process variable. And then the OP, I don't remember what is OP again. Yeah, I don't remember. Controller output, I think this is controller output.
It's in percent.
Controller output, yeah, exactly. So it's in controller output. And then the 9 is then the mass flow rate that goes through the that PSV. So this 9. So it seems to me that we start at 3.5, and then somehow there's this dip. I don't know. Maybe this is typically like a very strange calculations that HYSYS can do. Maybe I made a mistake somewhere, but I don't know, and I don't know how to correct this. So it's a bit like I don't know what happens. So and then I increase the pressure, and then it goes up, right? It goes up, and then when it goes up to 4.5, and then it will then open, and then hence this the flow rate at 4.5, because this was the zero, the flow rate that through the PSV is from zero, and then when the pressure is about 4.5, it goes up. So at this point we have to see where the pressure goes to 4.5, so somewhere there, and then the PSV goes instantaneously go up to release the pressure. So that's basically what happens, and then we can just rerun this and see. So 3.5, yeah. I think I have the strip chart with me. This is the graph. Um, 6.9 is the controller output, I guess. Yeah, 6.9 is controller output. Yeah. So it's not really thing to avoid confusion. We'll just delete this. Graph control pressure. This one. No. No, I can just remove this guy on alone. So it's just there. Okay, just bear with me. So and then the stream number 9, yeah, stream number 9 mass flow rate is then the basically the one that goes through the relay valve, and then we can see they're all at zero. Yeah, you can see this as well. So it's stream number 9. The flow rate is 0. This valve is closed. And then we have incoming 368, outgoing 368. So it's already in a steady state, as we see. As you see, it's a straight line basically. So it's steady state in nature. So what I did is, what we will do is that we will open this valve fully. Yeah, because now the valve is only 2%. So I will open this valve fully. So this is then 2%. The pressure here is 11 bar, 11.36, and then the set pressure is about 4.5, 4.461, and then 4.5 for fully open. So if we open this valve fully, the whole gas that is coming here, because it's a higher pressure, yeah, it will then go through the valve to the vessel. It will then increase the pressure of the vessel. So if the pressure of the vessel is reaches the set pressure of the valve, this valve will open, basically, yeah. So that's what we expect. So so that's what we do. I'll just fully open this and then click enter. I see. Negative pressure has been detected. I don't know why this comes. Values will be set to so I will attempt to continue. So this is, I think, the this guy, this tip. I don't know why. Yeah, I don't see this in symmetry. Maybe this is a glitch from HYSYS, I don't know. So click OK, and then we will see the pressure. Very strange. Yeah? The pressure is really like 0.6, 0.66 bar. So you can see this green one. See, pressure is already 6 bar, but then we don't have any flow yet. It's very strange. Let's check what happens. Yeah. Now suddenly it goes up.
Yeah.
One. No. No. It was just, I don't know, something happened. When we stop, it goes up. So when we stop, it goes up. I don't know. Maybe it's not updated. Yeah. Let's check what happens. So it says that valve is open, obviously, because we need it to be open. It has to open. But somehow this graph is not being updated. I don't know what happened. Maybe it's my laptop or whatnot. What I will do, I will just send this through the to the Skype and then see if you can open and rerun this. Okay.
All right.
I think that will be better.
Can you share the slides too?
Yeah. I don't. Let's check. Add file. Minute, yeah. Yeah, Aisha, you are recording this, yeah, right? Because I'm not recording.
Yes.
Okay.
I'm recording.
A minute, yeah. Where did I put it? This one. And then I will share you this one desktop. Enter. If you have any question, just ask. Yeah, a minute. For me, I don't have to save it as XML, right?
Yes.
Okay. This one somehow it doesn't work, or maybe the graph is not updated. But then if we stop this, we see that there's a flow. But if we run this, there's no flow. Very strange. I don't know. But we can see now the pressure is now dropping somehow, because it has to have a number, otherwise it cannot drop. So I don't know. Maybe this is the laptop problem for tonight. I don't know. So can you open the file?
Can you send first?
Oh, it's not sent yet. Okay, sorry.
All right.
Can you open?
Hold on.
Any questions so far? How to download HYSYS on computer? This one, how to download HYSYS on computer? Means how to download HYSYS means.
Can you contact me after today's class? I can assist you to download Aspen.
Very good. Is it downloaded already, Aisha?
Yeah, it's recalculating.
Recalculating. Okay, so I don't know what happens to my file. Let's just see what you have. If the vessel open 100%, okay. If the vessel, okay, minute. If the vessel, apa maksudnya ya, vessel terbuka 100%. Oh, valve. Okay. Sorry. Because the valve, there will be like a valve is then it's changing the pressure different. It's changing the pressure, yeah. So we have a high pressure here upstream of the valve, and then a lower pressure here downstream of the valve. So depending on how much is then the pressure drop, means we expand it, yeah. If we expand it from 11 bar to like maybe 11.36 bar into maybe 11 bar somewhere, and then we will not see any temperature difference. But if we expand it to a much lower pressure, sorry, if we expand it to a much lower pressure, we may see what they call, or what we call as a Joule-Thomson effect. So the gas will expand, and then it will then the experiencing a reduce in temperature. Yeah. Some gases, I think you can go to Wikipedia. Some gases they have a different phenomena. So instead of when we expand it, instead of having a reduced temperature, the temperature can go up. So I don't remember what the term is. Something that we can look up in Wikipedia. I don't know. I'm not clear. Because thing can go. Joule-Thomson effect. So when we throttle, yeah, when the flow is forced through a valve, when we throttle it, it will expand. If it expands, is there anything? They have what they call as the Joule-Thomson coefficient. So this one. So if the gas temperature is above this, below this, and above this, you can go read this again. Yeah, the inversion temperature, because I need to read this again. And then if it's below the inversion temperature, so we'll see what is then the inversion temperature, and then the gas will then cools down. So we will have a temperature lower at the downstream of the valve. If it's the other way around, that means we will have a higher temperature downstream of the valve. So depending on the inversion temperature, let's see. The Joule-Thomson coefficient. So this coefficient, the Joule-Thomson coefficient. So this guy made a lots of experiments, so he gets these coefficients, and then can be either positive or negative. Let's see this graph. So what we have is about 11 bar and 20 degrees C. Yeah? So 11 bar, 20 degrees C. So we have 11 bar is this 100, this is 20 bar. So it's somewhere here, 11 bar. And then 20 degrees C, so it's somewhere there. So we are in the, 20 degrees C means 20 plus 273 means 293 somewhere. So 293 Kelvin. So we are in this gas somewhere here. So in this case, in this part, yeah, because this is then the Joule-Thomson coefficient for nitrogen. So at this point, we have the coefficient larger than 0. So if the coefficient is larger than 0, that means if it's larger than 0, the coefficient is larger than 0, which is positive. That means when we expand the gas via a valve, the gas will then cool down. which means the temperature downstream of this valve, this temperature here will drop. As you can see, it is 21.1. Now it is 19.97. So there is a drop in temperature. So that's basically what this means, yeah. What is this Joule-Thomson effect? So you can see depending on the where is the thingy? So so each component they have this kind of graph. So depending on where we are, so if we somehow here, for example, so if we expand the gas through a valve, we'll get a higher temperature downstream of the valve. But if we are here somewhere in this region, we will have a lower temperature downstream of the valve. So that's basically what it is. So this gas, that cool gas, is then going to also cool down the vessel. I don't know. Am I being clear or no?
Doctor.
Yeah.
Can I share my screen?
Yes, please. So what happened to your screen?
So I think I found the reason why the PSV did not pop. You see, we have a pressure valve here that only it was set at 3.5, and so the this pressure vessel here did not actually reach 4.5 valve, which was
it has
set.
to. I mean, Aisha, can you move this dark that one? Kill it.
Because when I played around, this one I played around with this valve right. Sorry, this valve right here. I played around with the set point to be slightly above set point for this relief valve.
No.
You see that there are spikes of like the relief valve popping.
Yeah, but that is not the intention. So the intention.
Yeah, but the thing is, when I try to open this to 100%, it says flash fail. Let me try to reset this first.
Put it back to
It was 3.5. Okay, and then let's run.
Because the idea, yeah. So it's now a bit unstable. Let's wait for a moment. So the idea of a PSV is then to protect the vessel. So we have a pressure control valve, that VLV 101. So what it does is just to control the pressure at the set point that we want. So it doesn't protect the vessel. So it also not meant to protect the vessel. Yeah, so the goal is just to get that pressure to 3.5 according to what the set point that we apply.
Yeah.
So if the pressure goes beyond the set point, it is fine. But then the pressure should not go beyond the design pressure of the vessel. Otherwise, the vessel will break. So in this particular case, the remedy, not the remedy, what prevents the pressure to break the vessel is then the installation of the safety valve. So it has to open at the set pressure that we intend it to open. But nonetheless, okay, now try to open that valve again to 100%.
It cannot. Let me try.
Yeah, just try it.
Yeah, we got this.
And then go, click OK. And see, there.
We have some value.
Close. So we can see, see now in your case, you can see the graph is going up, yeah. But then you're reading in this. Can you see the table on the left, on the right, table 9?
Yeah.
So that mass flow is 0.
Yeah.
Which is very strange. See, I don't know, because now the pressure of the vessel shown by the graph is 1.773 somewhere.
It's dropping.
Yeah, it's now close.
And we have some value.
Yeah, so this if this calculation is correct, this is what we call as chattering. So the the valve is quickly open and close. So at some point, practically, it will break the safety valve, and then we will have a fluid leakage.
Okay.
That's what
This is bad
going to
news.
happen. But in the simulation, you can do whatever you want. Now I'm suspicious whether whether we did something wrong or there's something wrong with the HYSYS. I don't know, because
This is yellow.
yeah, if it's yellow means it's open.
Open.
Just double click on that, and then you will see. It's
Oh,
open,
valve is open.
and then if it's green, it's closed, but it's not really fully aligned. There's some delay somewhere.
All right, I see.
But at least you can see it now. See now the flow rate through the stream 9 is always 0, but then if you see on the graph, it has a flow, but not shown in the graph. Very strange. In the slide that I just sent to you, I did that. So it's perfect. So it's as what I would like to see it. But when we redo this, it goes high wire. I don't know why. So maybe we need to build this from scratch again.
Yeah.
But I think this is how we should do it in
You want to share screen?
Yeah, it's the same.
This is failing.
Yeah, I mean, that's very strange. I did not see this before.
What is this called again? Chattering.
Yeah, this quickly open and closing the valve, the safety valve is what we call chattering. So it's chatter. So it's really open and close, open and close very quickly. Yeah, it shows this yellow and dark and yellow and dark very quickly. So that means the valve is then, because in safety valve there is a spring. I think let's do a Google search here.
Share screen.
PSV. Okay, not this PSV pressure. Image. This one. So you can see if the pressure. So the vendor, they will adjust the spring in such a way that it will open when the pressure in this somewhere here below here is then the vessel that we want to protect. So if the pressure goes higher or reach the set point, that pressure is strong enough to force lift this spring. So this part will go up. So if this go up, that means the gas can then escape through the to this pipe, to the flare or whatnot. Okay. So if the pressure here goes up, and then this will open. If the pressure goes down, and then this will close. So if we see this valve is, if the valve is not designed properly, yeah.
Hello. Hello. Can anyone else hear me?
Yes, I can hear.
Oh, okay. Dr. Zulfan said his laptop suddenly stuck.
Yeah. Nah.
So Stila, if you want to learn anything, you can contact me, okay?
Okay,
Dr.
siap.
Zulfan, Dr. Zulfan said if you like want to learn about, example as of now, you want to learn about relief valve, this was actually requested. Ni sebenarnya saya yang request dia ajar. Tapi kalau kamu ada apa-apa yang kamu nak belajar secara spesifik, mungkin apa-apa yang berkaitan dengan studies kamu, bagi tahu je saya, nanti saya request dengan dia.
Oh ya. Iya Mbak Isya, oke.
Kamu dulu degree belajar di mana?
Itu tadi yang degree di UISI Mbak, yang di semen itu tadi loh. Kalau yang
master pun di
master
universiti
itu
yang sama?
tidak, di ITS.
Oh,
Iya.
okay. Good luck. Ija ni
Oke,
pun,
thank you.
yang kawan saya Fariza ini pun buat master sekarang.
Oh iya, di mana?
Di UTP juga.
Oh,
Universiti sama, Universiti Teknologi Petronas.
I see. Ambil penelitian tentang aspen kah?
Apa dia?
Ambil penelitian tentang aspen. Oh.
Ya.
Dulu waktu saya degree itu skripsinya tentang bioetanol.
Waktu degree guna aspen HYSYS juga?
Beberapa case ada yang disuruh pakai aspen gitu.
Faham. Sama jugalah. Yang ni memang kami belajar luar kelas lah, sebab dulu pun tak belajar secara mendalam pun kan.
Iya betul. Makanya ini saya baru gabung itu juga kayak baru banget ini saya belajar.
Ya.
Berarti ini Dokter Zulfan join lagi atau?
Dr. Zulfan. Dr. Zulfan ni dia bekerja di Petronas.
Oh.
Dulu dia lecturer di universiti kita orang. Cuma sekarang ni dia dah bekerja di Petronas dah.
Oh, I see. Iya, iya. Iya, keren banget Dokter Zulfan. Saya kenal beliau dari grup Telegram Teknik Kimia yang se-Indonesia itu.
Oh, ada sharing pasal ni kelas ni?
Iya, betul. Jadi langsung join gitu. Lumayan.
Hai.
Hai dokter.
Halo
Yes.
dokter.
So it's the time to replace my laptop now. Where was I?
You were explaining spring on relief valve.
Spring, okay. Recovery is all the recover. PSV. See? Restore. While waiting, I will show you this. This is the work that we did in symmetry. Basically. This is loaded as new. So what we have, can you see this?
Yes.
So basically, this is what we have here. So we have a column. We have the 3 reboilers, and then we have this one is simpler. The other one is simpler. This one, that one is quite complicated. This one. So this one is so we have 3 rebars as well, the column, and then we have the overhead flow rate. The overhead line goes through a cooling water condenser, and then it goes to the condensed part is then flowing to a reflux drum basically, and then the uncondensed part is then sent to the off gas. It has like a water, so it's a 3-phase separator, and then we have the liquid coming back to the column as a reflux. This one.
Yeah.
Yeah. So this is on the level control. So this flow rate is on level control. This to the water, it's also level control on the boot. The pressure in this line, which basically means the pressure at the top of the column, as well as the pressure throughout the column, is then controlled by this off gas valve. Yeah. So if the pressure goes up, means this has to be open. If the pressure goes down, and then this has to be closed. Yeah. So this typical control scenarios. And then from this line as well, the way we control the pressure is then we have the PSV here. So in this particular case, there are 3 PSVs installed in parallel. So I drew it only one, but there are 3. 1, 2, 3 next to each other in parallel. Yeah, 2A, 2B, 2C. So there are 3 PSV.
Hold on, doctor. I don't understand. 3 PSV meaning that the load are divided equally, or it's like if this
Very good.
doesn't work, the second will work.
The load is divided equally. So say for example when they size this, they have like I don't know, some numbers, and these numbers maybe for example, I just take a number, maybe 10,000, and then this valve, for example, they can only choose like for what is this, it's 10,000, and then they have, for example, here 4,000, 4,000, and 4,000.
Okay.
And so in total, when all of these three valves are fully opened, we have a total flow of 12,000. So that's enough to relieve this 10,000 flow rate requirement.
All right.
And then in the other column, they have 5 even. The other column is then they have 5. So they have 5 A, B, C, D, E. So they have 5 PSV.
Okay.
So depending on the load that we calculate, and then the sizing. So if we don't find the suitable PSV sizing, and then we can have like a multiple PSVs, or in most cases, if we have because we identify different cases, right? I think you see. Idea. When we go to here, I don't want to destroy this, but I think I don't know if you a minute, yeah. PSV sizing. I need to open the other one. So when we see I can just Google this, yeah, why not? PSV relief case. So this guy crawl. Now it's very easy to learn. You can just ask Google. Google knows everything. So this guy, it's good to have it here. Where are the cases? Cases. It's not shown. Oh, I missed it somewhere. I need this one. Define overpressure scenarios. So in these overpressure scenarios, we define several scenarios, and then we calculate how much is then the relief that we have to release. And then it could be many, it could be many scenarios. For example, the most often one being used is then the I will show you this one. So the most often one being used is that, for example, in this column, for example, if we have like a cooling water blockage, so there is no cooling water, so that means all of this vapor will not be condensed. All of the vapor goes to this reflux drum. It will then pressurize this. So when it's pressurizing these drums, it will then pressurize the whole line back to the column, and it will also pressurize this column. So that pressure we have to relieve it through the PSV. So that's one scenario. The other scenario is that, for example, they have this valve is then closed, so that means there is no reflux. So if there is no reflux, that means this whole vapor, all vapor that goes up, it will not be cooled down, and it will then create higher pressure here. So if this pressure is then higher than the set pressure, it has to be released through the PSV. And there's also another scenario like the pump shut off, for example, which has the same. I think it has the same consequence as the valve is closed. There's also some scenarios like, for example, and the steam. See if this steam is then fully open, and then we have the steam going in full power, heating up the column, and then it will then also then pressurize the column, and then it will see what the pressure is, and so on and so forth. And there's also like typically if the fire case, so we have a fire somewhere, and then this fire will then will then give like a heat radiation in the liquids in the reboiler and then the adjacent equipment. So it will then be vaporized, and then it goes up to the column, and then it will then pressurize the column, which has to be released. So there are many scenarios, and each of these scenarios, they will have a different load. Will have a different load to release. So some load is then bigger than the others, and then hence in some cases we have we need to select for example in this ABC we need to select A is that at a smaller size compared to B, and then B could be also a smaller size compared to C, depending on the cases. So for like a simple, like a small cases, only A is going to be open, right? And then if it's a bigger flow rate, and then maybe A, B, C will then open. So in that sense, we are preventing the valve from being open and closed, very often. That's what typically is happening. But then in this case, if you can see, this we did this in pen. So you can see, what we did is that we have a cooling water failure at 500 seconds. So it's all stable. At 500 seconds, this dotted line is then the cooling water. See, condenser duty. Condenser duty is doing fine, but at 500 seconds, we switch it off. It goes down to 0. And then the pressure, the solid line, the pressure will then going up. See the condenser pressure, and it's also the top pressure here, these two lines. So they're going up until it reaches the what we have is 24.5. So this is where the steam reboiler is then shut off. So this is then the steam reboiler, this shut off, but we do still have the other two reboilers. So this will then create the energy will then still supply the energy. Hence the pressure is still going up, and then when it reaches like 25.3 somewhere, the valve, the PSV will open. It will then release the gas, and then the pressure is then going to be dropping down. So that's basically what it is. See, this is then the PSV. So you can see at 500 seconds, the 500 seconds, the condenser fails, and then the pressure going up. But then at about 800 something, right? You can see at 100 something here. So we have a switch from going up to going down. So at this point, about 800 seconds, that's where the safety valves open. 3 safety valves. So it's about this 800 seconds. So about 800 seconds, the safety valves, all of them goes open, and then it will this is then the flow rate to the maximum, and then drops until here, close to 1,000, and then it suddenly goes to 0 again, which is then it's close to 1,000. So in this case, close to 1,000, it is already at the operating condition, so to say. What else? Yeah. See, you can see. In this case, you can see. This is another case, reflux failure, but I let it run until 2,500 seconds, and we can see it goes up and down, if we prolong this situation. And then to accommodate that, in this case, for example, so in this base case, we have 21.3 all A, B, C, D, E, 5 PSVs open at the same set pressure, 21.3. And then we have option 1. So option 1 means A opens at 20.7, and then B, C, D opens at 21.3, as it used to be. And then E is then opening at a higher pressure. So this is basically like 90%. This is 100%, and this is like a 110%. The same over here. So we have, instead of valve A only, we opened valve A and B at 90%, and then CDE at 100%. And then we can see them here, the performance, the pressure. And then the base case is solid line. Option 1 is then the small dotted line. Option 2 is then the longer dotted line. You can see at all goes up, and then but option 1 and option 2, some of them opens at 20.7 bar, right? So at 20.7 bar, so option 1 and option 2, they are opened. Option 1, because there's only one valve opens, it is not enough to relieve the pressure, so we can still see the pressure is still going up, but at a slower rate compared to this guy. And then the option 2, which has two valve open, the pressure can be released. You can see now. And in option 1, because pressure keeps going up, and then at this point, the other 3 valves will then open at this point in time, 21.3, and then it will then remove the whole gas, very quickly. Now you can see this is then the effect of removing the gas using 3 valves. This is then the effect of removing the gas using 2 valves. You can see the slope, yeah? It's more rapid compared to this one. And for this 2,500, there is no chattering for at least option 1, but there are like something like that, I guess. And then the option 2 is a bit more rapid. But the base case is the most rapid ones. So if you want to break PSV very quickly, and then you can just use base case.
Okay.
If not, then we have to be smart with this the setting of the PSV.
Okay.
Yeah. Okay, we'll stop until 45, yeah, because we start also a bit late. So far, do you have any questions? So let's see what happens. Yeah, now I restarted my laptop. So hopefully this is okay. Right, so we can see. So you can see from this report, there's no glitch, right? When we do this, there's when we do some failure, so there's no glitch. So the pressure goes up very nicely. So it doesn't go down. I don't know what happens to this HYSYS. We need to check them. Okay, so now let's do this. So nice and steady, and at 3.5 bar, right, as controlled. And then if we open this,
Oh.
it goes up, so it gives a very different result. I don't know what happens. It goes up and then it closes again very quickly, but then this guy is still opening, means the pressure should go up, but this is not. Yeah, this is not.
The
Red,
valve is still
very,
opening on the simulation. It's yellow.
right. So it's you can see the where is that thingy? Separator. Pressure. Oh, pressure. Oh, now I'm lost. No, this one the pressure. Bar. So it's not doing crazy jumpy thing, but it's not shown in the graph. It's very strange, yeah. I don't know, maybe something wrong in the installation or whatnot. I'm not really sure. Because it goes up and down, but doesn't. It's not visible here in the graph. It's very strange. So it doesn't really reflect the one that I just did and then sent to you in the PowerPoint.
Yeah.
While it is using the same file basically. I don't know what happened. Yeah, like many things in life, yeah, we can explain it. So I don't know. I think yeah, all of you, I think you can just try to do it on your own. Maybe you can create your own simulation, yeah, from scratch. At least now you know how to do this. At least this is how I do that, yeah. Because typically it's a T, and then we have this valve, the relay valve over there. So, very strange. If I close this again, what happens here?
I think there might be something wrong with the thingy.
Yeah, there must be something wrong. Hey, sorry.
With the strip chart, because I mean the simulation is running okay.
But the strip chart is not wrong. It's not right, yeah.
I guess.
Yeah, I think so. There's something is wrong either here or there. I think so. Otherwise, we won't be seeing this very strange how to call it? Very strange behavior. Let's see if I but now it looks okay. I mean, this guy is very crazy. So now it looks okay, right?
Yeah.
Align. So now if I change this to yeah, a smaller one, for example, M. See, you can see now it's changing, yeah, automatically. Instead of T is now I put M, and then we'll play this again. Wait for this 3.5. Yeah, this should be okay. 3.4. Open this again.
Oh, okay. There's some value there.
Yeah, see this one. So it opens. The control valve is also opening. You can see this blue one is then the control valve. This is opening because it needs to maintain the pressure here, but it's not strong enough. Hence the this guy is then helping it. And now the pressure, it goes up, but now it's not going down because we are releasing the gas from the vessel. So now it looks more reasonable.
Yeah.
Compared to the previous ones. I don't know what happened. Still opening, and then the pressure is now going down because we open the PSV is open. Now the control valve is now it keeps going up until it opens fully. But the pressure is steady at 6.2 bar, basically.
Yeah.
Now, because we have this fully open at very high pressure here, so it ends up only like we destroy the pressure somewhere here, and then it's just stuck to 6.25 bar. It cannot be, see, it's all steady, so we cannot reduce the pressure much more. And then the valve is already fully open. This guy is also open. There's nothing else.
We need another relief valve then.
And we need to have another relief valve, maybe. Yeah. It's just like too much gas coming in, so put it back to 2. But that's basically how we do this in a simple way. If you have if you can do a more complicated way in your own time, and then just have a practice with that. I still need to find some time to make the column simulation in HYSYS in dynamic, and then put the safety valve as what I did in symmetry. But it's basically the same approach. Yeah, we design this as we know it, and then we make it in dynamic, and then we have this T over there to make. That means in this case they have 5T or maybe 1T, but different. We have 5 outlets. 3 outlets in this case, 3 outlets for the PSV, and then 1 outlet to this guy. So 4 branches, and then we do the same simulations like what we are now doing here, to see what is then going to happen. But in this HYSYS, it gives these very strange results. I don't know, so I'm not really sure if I can trust the results from HYSYS. Yeah, this one I think we need to be clear on that. Or maybe I did something wrong. Yeah, but so that means I need your help to check the if we did something wrong in the input or the sizing of the PSV or not whatnot. So is there any question?
I'm good.
Good. Stella, ada pertanyaan nggak?
Sudah cukup jelas, Pak.
Ija, no Ija. Ija is there.
Yeah, Ija.
Perry, no question. Yeah, if there's no questions, and then I don't know. I'll see you next week. Next week, what do you want to discuss?
Maybe can we try to make a steady state using symmetry? I haven't really,
In symmetry, I don't have it in this laptop.
Okay.
But
We
it's
can.
basically the same, yeah. If you can do the simulation in HYSYS, you can pretty much do it in the other platform. You just need to adapt a little bit here and there, but then in no time you can do it in the other platform.
Mhm.
Do you have symmetry in your laptop?
I just contacted. I'm still. I just whitelist my laptop, so I haven't.
Yeah, so I don't have the symmetry as well on this laptop.
You can. I think you can contact Petronas ICT. They can install it for you.
I have it in my Petronas laptop, but not in
You
this
can
one.
download it at your personal laptop if you want.
Yeah,
Mm.
I'll see. First, I think I need to change my laptop first. That's the first
Okay.
thing to do. Otherwise, it will go crazy. Um, if there's no other questions, yeah, let me know. Yeah, next week maybe you can discuss among yourself, and
All
then
right.
we'll see what kind of topics that we can address next week.
Okay.
Uh, or maybe event scheduler. I think I remember event scheduler. Because what we did here in this in
Mm-hmm.
symmetry, what we did is that we use event scheduler. So for example, yeah, so I did not open the valve at 500 seconds and then manually. So I made the event scheduler. So we kind of like a program it at 500 seconds. The condenser is off, and
Mm-hmm.
then when the pressure goes up to 24 and a half, this reboiler is then off, and
Mm-hmm.
then and that's it. That is then the events that we created for these simulations.
Mm-hmm. Yeah, we can
So
try to do that on Aspen.
at least for next week.
All right. Okay.
Okay, yeah. So
All right.
share the recording here, yeah, Aisha.
Yeah, yeah, yeah.
Okay. So
All right.
thank you. See you next week then.
All right. Thank you, doctor.
Yeah, thank you. Bye bye.
Thank you, dokter.